Hello, good morning everyone. I am myself K. Narsimurthy. I am presently working as an assistant professor in Government First Grade Women's College, Tumkur. Today I am going to present 38th video for the second semester students of Tumkur University. So in my previous 30 videos, I have covered the first two units, which are electrostatics and magnetostatics. I have covered these two very important topics, electrostatic as well as magnetostatics. And after 31st video, I have started with the magnetic materials, and in 5 hours I have covered these magnetic materials. Okay. From the 36th video, I have started a new chapter which is called Maxwell's equations. Okay, right. So when we come to the Maxwell's equations, so Astor discovered a magnetic effect of electric current, where he says that a current carrying conductor will produce a magnetic field. Whereas this Faraday in this 1831 he discovered the induced current. He says that when there is a change in the magnetic flux linked with a coil, an EMF or a current is induced in it. So magnetic field produces a current, and the current will produce a magnetic field. Now these two quantities are no way separate entities. They are the two aspects of same subject. The two fields, electric field and the magnetic field, are no way separate entities. They are the two aspects of the same topic. Okay. Now we have an electromagnetism which deals with both these electric field and the magnetic field. Now they coexist. Electric field and magnetic field coexist. Right. So I have derived one Maxwell's equation. Maxwell's gave 4 set of equation. Okay. This behavior of electric and magnetic field is governed by these 4 important set of equations which are given by the Maxwell. Right. And then I have derived in the previous video the first Maxwell equation. Maxwell formulated these laws, the laws of electrostatic and magnetostatics, like Gauss law, Ampere's law, and the Faraday's law. He modified these laws into the 4 set of equations, Ampere's law as well. So these 4 important laws he modified into 4 different set of equations, and they are called Maxwell's equations. Now I have explained one Maxwell equation in my previous video. Today I am going to explain 2 more Maxwell's equations. These are very simple equations, and the derivation is also very simple. Right. Now the second Maxwell equation is div dot B, divergence of B is equal to 0. So we are going to derive this divergence of B equal to 0, and that was the second Maxwell equation using the Biot-Savart's law. Now we'll take the Biot-Savart's law. What actually this Biot-Savart's law says? Biot-Savart's law says that the magnetic field due to a current element, magnetic field at some point P due to the current element, is given by mu naught by 4 pi IDL sin theta divided by r square. I have explained very clearly about this Biot-Savart's law in my the previous videos while discussing the magnetostatics. Okay, so where I have explained that the magnetic field at some point P due to the current element is directly proportional to length of the current element dl and the current flowing in the current element I, and inversely proportional to square of the distance between the current element and the line joining the current element and the point P, where I can write B dB proportional to IDL sin theta divided by r square, where I have to add some constant to equate it. So I have added this constant mu naught by 4 pi. Now the magnetic field at some point P due to the current element is dB equals to mu naught by 4 pi IDL sin theta divided by r square. So if I have to write in vector form, it is I into dl cross r cap divided by r square. Or if I want a vector in the numerator, it is I into dl cross r vector divided by r cube, because I am multiplying and dividing by both by r. So therefore a numerator I will have an r vector, and denominator r square becomes r cube. So it is I into dl cross r vector divided by r cube. Otherwise you can write it as I into dl cross r cap divided by r square. So r cap by r square is also fine, or otherwise if you want to write a vector, it is r vector by r cube is also okay. So both the way you can express the magnetic field using this Biot-Savart's law. Okay, yeah, I have told you what would be the direction of the magnetic field. It will be perpendicular to both the length and the r vector. Okay, right, I have explained all this, the Biot-Savart's law equation. Now I have taken as mu naught by 4 pi I dl cross r bar divided by r cube. Now that is only due to a small current element. That is why I have taken that as dB. Now what I want is a magnetic field due to a whole conductor which carries a current. Then if I want a total magnetic field, I have to write B, and I have to integrate that equation. I have to integrate this I into dl cross r divided by r cube. Okay. Now the magnetic field, total magnetic field for whole conductor which carries a current I, according to Biot-Savart's law, is mu naught by 4 pi line integral of I into dl cross r divided by r cube. Okay. So I have mentioned the total magnetic field in the equation 1. It is the total magnetic field due to the current in a whole conductor. Now what I am going to do in the next step is I will take the divergence on both sides. So left side will be the divergence of B is equal to constants. I will take it outside, mu naught I by 4 pi. Even I is also a constant. Okay. So only variable is length L. Okay. So it will be a divergence of dl cross r vector divided by r cube. So let me call it as equation number 2. So I have taken the magnetic field from the Biot-Savart's law, and after that I have taken the divergence on both sides. Right. Let me move further. Now we have an identity, a vector identity, which is divergence of A cross B. Students, you all know this vector identity. Okay. In mathematics, you have come across this vector identity. The divergence of A cross B can be written as B dot curl of A minus A dot curl of B. Okay. So this you have used the identity in the mathematics. So we are taking the identity and we are applying for this equation number 2. Equation number 2. So in the equation 2, I will get a term like dl cross r vector by r cap. For this, I am applying divergence and I am using this identity, and I am writing it as, I have to write a second term first. R by r cap is a second term. Okay. Dot of curl of first term. Curl of first term is dl minus first term. First term is dl dot curl of second term. Curl of second term is r by r cube. Okay. So I have written this identity. I have applied this identity to divergence of dl cross r vector by r cube. Okay. Let me simplify this further. Left hand side will remain same. Here in the right hand side, r cap by r, instead of r vector by r cube, I have told you that you can write it as r cap by r square. You can write this as r cap divided by r square. Yeah. Right. So r vector by r cap, r cube, r you can write it as r cap by r square and curl of dl minus dl cross curl of, again that r vector by r cube can be written as r cap by r square. So because I know that r vector is r into r cap, r vector is r into r cap, that is what I am using, and I am substituting for r vector as r into r cap. So 1 r cancel with the denominator. I will left out with r cap by r square. Okay. So I have used the identity, the mathematical identity, which is divergence of A cross B, that identity I used for divergence of dl cross r vector by r cap, and I have done a very small substitution, that is r vector is r into r cap. So I got this equation. I am going to substitute back this equation. Right. Now consider RHS, since dl is not a function of coordinates of a field point. It is not at all a coordinate of field point. Field here is the magnetic field. So this is no way connected to a magnetic field. The dl is absolutely a length. This length, it is no way connected to a magnetic field. It is not at all a coordinates of magnetic field. So therefore, doing curl of this length vector is absolutely zero. Okay, because when you do a curl for a rotational vector, it has some meaning. It has some non-zero value for a rotational vector. But dl is a length of the conductor. It is not a rotational vector. It is absolutely a length of the conductor. When you do a curl of that, it will be zero. This dl is no way connected to the field. It is not at all a coordinate of magnetic field. Therefore, this curl of dl is zero. The term which I come across here, the first term here in the right hand side, curl of dl is zero. I have left with only the second term, which is minus dl dot curl of r cap by r square. Alright, let me do further. Now I know what is this. 1 by r square can be written as divergence of minus 1 by r. What is actually the divergence? It is dou by dou r. Divergence is just a dou by dou r. So if I differentiate minus 1 by r square, it will be 1 by r square. Okay, so 1 by r square can be written as dou by dou r of minus 1 by r. Got it? So 1 by r square can be written as dou by dou r, means partial differentiation of minus 1 by r. Correct. So dou by dou r is our divergence. Divergence is dou by dou x plus dou by dou y plus dou by dou z. It is nothing but dou by dou r. So dou by dou r of minus 1 by r, which is gradient of minus 1 by r. For scalar it is a gradient. For vector we call it as a divergence. So it is gradient of minus 1 by r. Okay, right. So 1 over r square can be written as gradient of minus 1 by r. So I have a quantity in the second term of that big equation. It's curl of r cap by r square. It is curl of gradient of minus 1 by r, because 1 by r square is gradient of minus 1 by r. So it is curl of gradient of minus 1 by r, which is equal to 0. Okay, so what I know is the curl of gradient is 0. So you cannot do curl and gradient. So this gradient means divergence kind of a thing. It tells you how much it is diverged, but curl says that how the vector is rotating. So if I do the curl and divergence together, it will be 0 for any vector, for that matter. And for any vector, if you do curl and divergence together, it will be 0. Curl says a rotational kind of a thing. Divergence says how it is diverging. So if you do both the things for a vector, any vector for that matter, it is a rotational or an irrotational vector, the curl of gradient will be 0. Now the curl of grad is 0. So curl of gradient will be 0. So second term which we got here is also 0. The curl of r cap by r square, which is equal to the curl of gradient of minus 1 by r, which is again 0. So first term is also 0, because dl is not a coordinate of the field, magnetic field. It is not a coordinate of magnetic field. So second term is 0, because curl of gradient of a scalar quantity is 0. Therefore these two terms are 0. Therefore divergence of dl cross r by r cap is 0. Right. So I got both the things 0. Now let me go back and see the equation 3. So this is what the equation 2 is. So divergence of dl cross r cap, which I calculated dl cross r cap, I got these two terms. Both these two terms are going to be 0. Why both these terms are 0? I told you that L is not a coordinate of magnetic field, so you cannot take a curl for that. Even if you take it, it is 0. And here it is curl of divergence of a scalar is 0, therefore this quantity is 0. So both this first and second term here is 0, means the entire term is 0. So divergence of dl cross r by r cap is 0. I mean to say the right hand side of the equation 2 becomes 0, because the thing which is inside the integral, the quantity which is inside the integral is going to be 0. Therefore right hand side is 0. I mean to say the divergence, go back. So this is 0. Divergence of dl cross r by r cap is 0. Therefore the equation 2 becomes divergence of b becomes 0. So this is the Maxwell's second equation, second law of second Maxwell's equation. This is in a differential form. We more frequently use the differential form rather than the integral form. So this is the differential form of second Maxwell equation, which is divergence of B is equal to 0. Right. Now if I do a integral form, let us take a volume integral of this equation, volume integral of divergence of B dV, which is equal to 0. Now what I'll do is I'll take a Gauss divergence theorem, which converts surface integral to volume integral. So surface integral of B dot ds is equal to volume integral of divergence of B dV. So I'll substitute in the above equation. So then that equation number 4 becomes surface integral of B dot ds will be equal to 0. Okay. So this is the Maxwell second equation in the integral form. So divergence of B equals to 0 is an differential form of an Maxwell second equation. So surface integral of B dot d equals to 0 is the integral form of the second Maxwell's equation. Right. Now let us understand some physical significance and physical meaning of this second Maxwell equation. Net outward magnetic flux through a closed surface is equal to 0. Net outward magnetic flux. Look at the left hand side, which is surface integral of B dot ds is a net outward flow of magnetic lines of forces over a surface S, and that is going to be 0. Net outward flow of magnetic flux over a surface is equal to 0, and the net flux lines are continuous, forming a closed loops, implying that there is no source of sink or there is no source or a sink in the case of magnetic field. Okay, so there is no net outward flow of magnetic flux from a fixed surface. I mean to say the magnetic flux lines are continuous, forming a loop. They forms a closed loop. Okay, so here it means to say that there is no source or there is no sink in the case of magnetic field, but it is there in the case of electric field. The source of electric field is the positive charge, and the sink for the electric field, I can say it is a negative charge. But that is not the case in the magnetic field. So if you take a magnetic field, the field lines are continuous, forming a closed loop, whereas that is not the case in the electric field. These electric field lines of forces are straight lines which are going out, which are coming in. Okay, so here it is a closed loop. The magnetic flux lines are the closed loop in the case of magnetic field. But again, this fact rule out the concept of monopole existence. So I can say that the magnetic monopoles cannot exist because there is no source here, there is no sink here in the case of magnetic field. So it is evident that monopoles does not exist. The magnetic monopoles does not exist. I mean to say the North Pole will not exist alone, or South Pole will not exist alone. So if you want to create a magnetic field, you need to have both North Pole as well as South Pole, because these lines has to make a closed loop. Just from the North Pole, North Pole cannot exist. The monopoles cannot exist. So This fact rule out the existence of monopole. This fact rule out the existence of the north pole alone or south pole alone. They exist together. These poles of the magnets, north and south, they exist together. Okay, so monopoles does not exist in the case of magnetic field, whereas that can happen in the case of electric field. Even a positive charge can exist in the case of the electric field. Negative charge can exist in the case of electric field. But here it is not possible in the case of magnetic, because it is a rotational field. This magnetic field is a rotational field, so therefore that cannot be possible. So here there is no source or a sink in the case of the magnetic field. Right. So let us go to the next derivation. So next Maxwell's equation, which is the third Maxwell's equation. I am going to derive this curl of an electric field is equal to minus dou B by dou T. B is a magnetic field. The curl of an electric field is equal to negative differentiation of magnetic field. This I am going to derive with the help of Faraday's law. Now, according to the Faraday's law of electromagnetic induction, induced EMF. How an EMF is induced according to Faraday's law? Suppose if there is a change in the magnetic flux linked with a coil, then EMF is induced in the coil, or a current is induced in the coil. Okay, so what is the quantity of EMF is induced in the coil? The amount of EMF induced in the coil is equal to the rate of change of magnetic flux. E is equal to rate of change of magnetic flux. And I am putting the negative sign. It tells you that the direction of induced EMF is opposes the cause for the production. The induced EMF opposes the change in the magnetic flux. This is according to the Lenz's law. So Lenz's law very clearly gives us the direction of induced EMF, which says that induced EMF opposes the cause for its production. Induced EMF opposes the change in the magnetic flux, which is the real cause for the production for the induced EMF. Right. So I can write an equation according to the Faraday's law was E is equal to minus d phi by dt. It's dou phi by dou t. This is the equation 1. I have written according to the Faraday's law of electromagnetic induction. Right. Phi is the electric flux. Phi is the magnetic flux. This flux, magnetic flux phi, is equal to surface integral of B dot ds. Phi is the surface integral of B dot ds. I have been using this equation. Earlier I used to use for an electric flux. So electric flux is the line integral of E dot dl, where I am using the same thing for the magnetic flux. So magnetic flux phi is equal to surface integral of B dot ds. So magnetic flux phi is the surface integral of B dot ds. Alright. Now equation 1 becomes the E, which is equal to minus of d phi by dt, where for the phi I am substituting as surface integral of B dot ds, which is the magnetic flux. Now I can write this as minus surface integral of dou B by dou t into ds. So let us call it as equation number 2. Now the induced EMF is what actually the work done in taking an unit charge once around a closed loop in an electric field. That is what the EMF, that is what the definition of EMF. It is nothing but the work done taking an unit charge one round in a closed loop in an electric field. So I can write this EMF as line integral of E dot dl. From the basic definition of induced EMF, I can write this as line integral of E dot dl. It is nothing but the work done. So work done is E dot dl. E is the force. E is the electric force. Force means the force experienced by the unit positive charge is E. So force into displacement is nothing but a work done. If I have to take a total work done for one complete loop, taking a charge for one complete loop, it will be line integral of E dot dl. So this work done is nothing but EMF. That is what we call it as EMF. EMF is the work done in taking a charge one round in a closed loop. So I can write this EMF work done as line integral of E dot dl. That is equation number 3. Now from equation 2 and 3, let us do equation 2 and 3. Alright, just a minute. Yeah, now what I am going to do is I am substituting this line integral of E dot dl as an EMF. If I do that, so our equation becomes line integral of E dot dl is equal to minus surface integral of dou b by dou t dot ds. Okay, so this is from both the equation number 2 and equation 3. So both are the EMF, so I am equating these two. So line integral of E dot dl is equal to minus surface integral of dou b by dou t dot ds, equation number 4. Now I am applying a Stokes theorem here. What Stokes theorem says is it's a line integral of a vector is equal to surface integral of curl of that vector over a closed path. Over a closed path, this line integral of a vector is equal to curl of a surface integral of curl of a vector. So it is line integral of E dot dl is equal to surface integral of curl of E into ds. So same thing I am applying in the equation number 4. If I substitute that in the equation 4 becomes surface integral of curl of E dot ds is equal to minus surface integral of dou b by dou t dot ds. So both side I got surface integral. Now these quantities which are in the left hand side and the right hand side, now these quantities are inside a surface integral. Now I can easily equate these two quantities. So I can say this curl of E is equal to minus dou b by dou t. Okay, because both are surface integral, therefore I can write curl of E as minus dou b by dou t. So this is the Maxwell's third equation, and this is the differential form of Maxwell's equation. Alright, now here let us go and find the integral form of Maxwell's equation. It is simple that you take a surface integral on both sides. Take a surface integral of this Maxwell's third differential form of Maxwell's third equation. The surface integral of curl of E ds is equal to minus surface integral of dou b by dou t dot ds. Okay. Now again I am applying a Stokes theorem here. So line integral of E dot dl is equal to surface integral of curl of E ds. So that I am applying in the equation. So equation 5 becomes, instead of surface integral, now I am changing it to a line integral according to that Stokes theorem. So line integral of E dot dl is equal to minus surface integral of dou b by dou t dot ds. This is the Maxwell's third equation, and that is the integral form of Maxwell's third equation. So I have derived the two important Maxwell's equations, and again I have derived an integral form of Maxwell's equation as well. Now if I at all I have to analyze the final equation, it says that EMF around a closed path is equal to rate of change of magnetic flux linked with the path. Okay, so EMF, let's go back and see the differential form. Go back and see the not that. So Maxwell's third equation is this: curl of E is equal to minus dou b by dou t. Okay. Now it says that EMF around a closed path is equal to rate of change of flux linked with the path. Okay. So it is minus dou b by dou t. So change of magnetic flux is minus dou b by dou t. So curl of E is kind of an EMF. EMF is equal to a change of magnetic flux. And negative sign over there, minus dou b by dou t, negative sign indicates that the polarity of induced EMF is such that it opposes that any change in the magnetic flux. Again the Lenz law. This is in accordance with the Lenz law. The negative sign in the Maxwell's equation, Maxwell's fourth equation, tells us that the induced EMF opposes the change in the magnetic flux in the coil. Okay. Overall I can say EMF is the change in the magnetic flux, and negative sign is what the indicates that the EMF opposes the change in the magnetic flux. So this is all about the two Maxwell's equations. So finally I have completed three Maxwell's equations. One I did in my previous video, and today I have explained two more Maxwell's equations, and now only one Maxwell's equation is left out, that I am going to cover in my next video. So thank you very much.